In this lecture, we're going to discuss the results about the comparison of two IMM configurations with the baseline Kalman filter in this realistic ATC problem. We have a table coming up in a moment where we have the position estimation errors in the psi and eta coordinates combined, so the full position error in the horizontal plane. We have a maneuver detection delay, which is the latency, measured in sampling periods from the maneuver onset time to the first time that the probability of the uniform motion mode falls below 0.5, namely the maneuvering model or mode probability is above 0.5, it dominates. probability error denotes the steady state probability of the maneuver modes during uniform motion, and it should be as low as possible. So this is the estimator calculated probability that the mode, the uniform motion mode, is not in effect, while in truth it is. We'll see that the IMM-CT coordinated turn configuration of the IMM has a peak RMS position error during the mode of flight change that is almost 20%, 25% below the raw measurement error, and 50% RMS error reduction during the uniform motion. And we'll see that the speed estimation error is 1% of the aircraft speed, which is a pretty good number, and the detection of the maneuver is also relatively quick, 2 scans, namely 1 scan delay for both turns in the target trajectory. So, as you can see, the Kalman filter is showing a position error peak about the same level, 141, this is 143, 141 is 100 times square root of 2, the RMS error with each coordinate having 100 meter error before filtering. These are the raw observations. IMM-R is a little bit below that in peak error, but IMM-CT is substantially below it. The uniform motion position error is 123, which is below the 141, but not much below, and you can see the significant reductions that the IMM obtains. Clearly, this is a compromise design with a larger process noise in the single mode-based Kalman filter. We would get possibly a slight reduction here, but at the cost of an increase here. So this is why the selection of the value for the process noise was done as indicated before. And we have other errors. The peak speed error, again, it's very significant in the Kalman filter. Even the IMM has about 9, and the IMM-CT is substantially lower. Again, clearly the IMM is superior, and the detection delay for the IMM-CT is 1. If the maneuver starts, say, at time k, the first time you could detect it is k plus 1, but the IMM-CT would detect it at k plus 2, which means the delay is 1 past the earliest possible detection. IMM-R takes several additional steps, and the uniform motion probability error is in percentages 3, which means this was the probability error, the steady state probability of the maneuver mode during uniform motion, which means when the target is not maneuvering, what is the probability attached to the maneuvering mode. And again, it's fairly small, but even smaller for the IMM-CT. Next, we'll see the root mean square position errors, again combined, so the total horizontal position error for the IMML and IMM-CT compared to the baseline Kalman filter. And there is an initial large estimation error because the two models were assumed to have equal probability. Initially, obviously, one can set the probability of the maneuvering model low at the beginning. So this really doesn't matter, but you can see the same pattern with the Kalman filter largest, the IMML next, and the IMM-CT strictly below it. So, in summary, the IMM-CT has peak RMS errors around 110 meters, significantly better than the single measurement position RMS error, which is 141 meters. And when the aircraft is not maneuvering, the RMS error is down to 70 meters, about 50% RMS error. It will be down to 30%, a 70% reduction in the mean square error. And the Kalman filter has a peak RMS at just around the level of the raw measurement, 143, but it does not go in the intervals of uniform motion much lower. It goes down only to about 120 meters. And again, if you want to reduce the error in the uniform motion intervals, this will be at the cost of a significantly higher peak error. This would require lowering the process noise. So that's the compromise that always one has to do when you use a single model based filter. Clearly the IMM-CT is superior in all respects to the IMML and much superior to the Kalman filter in this case. We have next the evolution of the mode to the maneuvering mode probabilities for IMML and IMM-CT to show the detection capability for the two configurations of the IMM. Both the 1 degree per second and 3 degree per second turns out the IMM-CT detects quite rapidly. 2 sampling times after it starts, the minimum being 1, so the delay is 1 for the IMM-CT. Another important issue is the sensitivity of the IMM to the design parameters. We have covered the selection of the design parameters, and as far as sensitivity is concerned, the answers will be empirical. However, the news is pretty good because it's not very sensitive, but there's one important thing to remember. When the IMM uses several linear models with different process noise variances, a large ratio of these variances is needed. Namely, the high variance should be quite a bit higher than the low variance. Otherwise, the filter cannot distinguish between the two models. So the models have to be sufficiently separated, and there is no point in using 3 or 4 models, low, medium high, and high, for example. A trivial case would be if the two models really are the same, the IMM becomes just an unnecessarily complicated Kalman filter. Now, the jump probabilities in the Markov chain, that's the maneuver onset probability, the 1-2 term in the Markov chain transition matrix, can be 5% or 10%, and we get pretty much the same results. Overall, the sensitivity of the performance to such variations in the transition probabilities are moderate. One other problem in real systems, sometimes we don't have fixed sampling intervals, it's variable, and therefore it has to be accounted by taking not fixed probabilities like we indicated here, but probabilities that depend on the sampling interval or the revisit time. We can have different situations, and this is discussed in the literature with a proper reference. So, the main findings from this example can be summarized as follows. The Kalman filter is clearly inferior to any reasonably designed IMM estimator. The accuracy of the turn rate estimate is not very important as far as the quality of the position, speed, and course estimates are concerned. It turns out that a closer look at the results shows that the turn rate estimate is not very good. Nevertheless, just having it helps the remaining 4 state estimation errors to be significantly lower. And also helps in the timely detection of the maneuver. The IMM-CT estimator is the best choice for tracking maneuvering targets with its capability to track both the linear motion, the nearly constant velocity or perfectly constant velocity, as well as the turn motion of the target. When the aircraft is in the nearly constant velocity mode, the estimates given by the filters based on the nearly coordinated model have little effect on the overall combined estimate, because we have an interaction between those filters and each will provide estimates to the other. However, there will be small weights. The interaction probability essentially leaves out during the one mode the estimate from the filter for the other mode. So when the aircraft is in uniform motion, the filter matched to the uniform motion model is dominant, and the IMM relies mostly on it, so it doesn't matter what's coming out from the filter for the maneuver, the CT model filter. Once the aircraft starts to maneuver, the filter matched to the coordinated turn model takes over rapidly, and it leads to a significant reduction in the peak estimation error, as we have seen. And the IMM-CT estimator performs better than Kalman and IMM-L during maneuvers. This is where it has the biggest advantage. Nevertheless, it is remarkably accurate in its ability to reduce the errors during the uniform motion as well. One could have considered a noise level switching version of the Kalman filter with one model at a time. This is a hard switching as opposed to the IMM-L, which does soft switching. This would amount to running a filter with a low variance process noise during the constant velocity portions of the trajectory, and following a maneuver detection, switching to filter with a high level process noise. However, this is not practical because we have a very short duration of the maneuver. Now, in this system, there is another problem. The origin of the measurements is uncertain, and the switching technique, this is the hard switching technique, is prone to making errors, so it is inadequate. Whenever we have measurement origin uncertainty, the data association problem comes in, and it can be meshed. Systematic data association techniques can be meshed easily with an IMM, and we can have much more reliable estimation in that case than if we rely on hard decisions. So remember, the IMM does soft decisions between maneuver and no maneuver. So the hard decision is prone to more errors. However, we have to remember that the nature of maneuvers is such that they are not zero mean white random processes, as the assumptions of the Kalman filter require. Therefore, we cannot expect any of the filters to be perfectly consistent. No matter how well you design it, there is no exact model for what's happening there. The judgment as to which estimator design is best is somewhat subjective, and in general, it should take into account the following, and these are the criteria for a designer to select the parameters of those filters. One thing that we care about is obviously the performance, the RMS errors in both position and velocity, or speed and course. There are two errors. There's a maximum error and there's an average during uniform motion. So these two have to be considered. The other consideration is desire for filter consistency, namely the covariances have to be compatible with the errors. So the errors have to be compatible with the filter calculated covariances. Last is the complexity of the implementation, which is not very significant since computation is pretty inexpensive these days. Nevertheless, there is a coding issue and a reliability of the code and so on. So clearly we will not get perfect consistency, so we should have some compromise between consistency and RMS errors. So overall, for this particular problem, the IMM-CT is the best choice. And similar results were obtained on actual real data from the FAA radars. Here is another issue. We discussed problems where we showed that the IMM is superior to Kalman filter. There are still not, we have not yet discussed when, in what situation this happens. So the topic for the next section is if we can find a limiting boundary above which an IMM is desirable, below which a Kalman filter, a single model based state estimator, is acceptable. It turns out there is such a limit, such a boundary, and we'll discuss it next. We have seen the design of an IMM estimator for a generic air traffic control problem, and the IMM clearly performs significantly better than a Kalman filter. Specifically, an IMM with a modest number, only two filter modules, a white noise acceleration and a coordinated term model, yielded 50% reduction in RMS position errors versus the Kalman filter. And this is due to the adaptive bandwidth or the dynamic range capability of the IMM estimator, namely its ability to handle uniform motion, in which case it acts as a narrow band low pass filter, as well as high frequency maneuver motion, in which case it acts as a wide band low pass filter. Kalman filter for such models is always a low pass filter, so the question is what is the bandwidth? So what the IMM really accomplishes is a self-adaptive variable bandwidth filter depending on the circumstances. When we use a coordinated term model, this is a specialized filter which is a wide band but for a special type of motion. So the question is the following. When is an adaptive estimator, in particular the IMM estimator, necessary? Based on pure intuition, the higher the uncertainty, the higher the maneuverability of the target, the more versatile tracker, like the IMM, is needed. So next we'll present an answer to this question using some simulation-based estimation results. What we are going to show is that the choice between a single model-based Kalman filter and a multiple model tracker, like the IMM estimator, depends on the maneuvering index lambda of the target defined in Chapter 6. Namely, what we'll show is that above a certain maneuvering index threshold, the performance of the IMM estimator in terms of its errors is significantly better than that of a Kalman filter, and therefore the IMM is recommended above that particular maneuvering index. If the target barely maneuvers, either nothing, lambda 0, or a small lambda, then an IMM is not necessary. If the target sometimes has lambda equal to 0 or nearly 0 versus a large lambda, then an IMM is appropriate. The question is, what is large? And this will be answered next. So the test scenario based on which we evaluate when a Kalman filter is necessary or is sufficient or an IMM estimator is better is as follows. We have a sensor that measures here two-dimensional Cartesian position with RMS errors, measurement of standard deviations, 100 meters in each coordinate. The revisit interval is t 5 seconds. Initially, the target will move with nearly constant velocity for 60 seconds. Process noise standard deviation 0.2 meters per second square with a very small maneuvering index, 0.05 in each coordinate. So we have a white noise in this case perturbing the motion. Following this, the target executes a series of 3 maneuvers. Each of these will last 60 seconds and will have a fixed maneuvering index lambda with corresponding, again, white process noise, 0 mean white process noise, and these intervals are interleaved with non-maneuvering intervals, again, 60 seconds with a very low lambda. And we leave this lambda open and see when this maneuvering lambda, the high lambda, is going to be a reason to choose an IMM over a Kalman filter. So the level of this maneuvering lambda is varied from 0.1 to 2.5. You can see 0.1 is only about twice, so just slightly above the non-maneuvering case. This is a typical case because turbulence, there's no such thing as a perfectly constant velocity motion typically. So the process noise standard deviation ranges for this range of lambda from 0.4 to 10 meters per second squared. That's 1G, that's pretty heavy. And we use the above values for the measurement noise, standard deviation 100 meters and t 5 seconds. And the performance of the trackers based on a Kalman filter and an IMM estimator, and this is an IMM-L, are evaluated using 100 Monte Carlo runs for each of these maneuvering index values. So we have this, the high, and this, the low, and we have to see beyond what threshold the high has to exceed in order to have justification for the IMM. The filters were, the Kalman filter was a second order white noise acceleration model with sigma v corresponding to 0.8 of the maximum process noise standard deviation during the maneuvering intervals, which means it was a compromise, close to the maximum but not quite at the maximum. And the choice was made in order to retain ability to track both maneuvering and non-maneuvering intervals, and other values of sigma v like 0.5, 0.6 yielded similar results. The IMM estimator had 2 white noise acceleration models. One was with a low process noise, which is the same as what the non-maneuvering intervals had. The other was using a high process noise corresponding to the maneuver process noise standard deviation. And the mode transition probabilities were 0.9 to stay not maneuvering, 0.1 to start to maneuver, and if it maneuvers, continues with 0.9 and gets out of it with 0.1. These correspond to a sojourn time of about 60 seconds, which is what the problem had, based on the 5-second sampling interval. We have, in a figure coming up in a moment, the peak position and velocity errors obtained with the 2 estimators. It seems very clear that both estimators provide the same peak estimation errors up to lambda equal 0.5. This is the high lambda. While beyond that value of lambda, the IMM is significantly superior in terms of providing lower estimation errors. And then we'll see the position and velocity errors overall across both maneuvering and non-maneuvering intervals. So these are the peak errors, and up to 0.5 they are about the same. Obviously, as you have more noise and the IMM does have that particular lambda in its maneuvering mode filter design, there is an increase, but it's low, while the Kalman filter has significant increases in its errors, both in position and in velocity. The overall estimation errors that's averaged over the entire interval, that includes both maneuvering and non-maneuvering intervals, shows pretty much the same pattern. Up to about 0.5 the difference is pretty negligible. Beyond that it becomes significant. We will see next the position and velocity errors during only the non-maneuvering intervals. And these errors, we can see that the IMM has them almost constant, whether those obtained by the Kalman filter significantly increase with lambda, because the Kalman filter is unable to provide the noise reduction during the non-maneuvering intervals, because it is adapted, or it is a compromise, and as the lambda is larger, the IMM becomes a higher bandwidth filter. Therefore, it is tuned to almost the maneuvering intervals, and its performance significantly degrades during the non-maneuvering intervals. And this is a direct result of the Kalman filter's lack of adaptive bandwidth capability. In contrast, the IMM estimator is able to maintain the noise reduction during the non-maneuvering intervals, even with higher levels of target maneuverability, because it adapts the weights given to the two filter modules, the mode probabilities, and therefore gives consistently better results. So the adaptivity of the IMM is remarkable in this case. So the uniform motion RMS estimation errors can be seen here. Again, they go up, and same for velocity. And we have this again in figure 4, where the RMS errors during the maneuvering intervals are shown. And even though the Kalman filter's noise levels were adapted to the increasing maneuverability, it still cannot match the IMM estimator's performance levels. So the breaking point is again around 0.5. These results indicate that below 0.5, the Kalman filter and the IMM estimator perform equally well, and there is no need for an IMM. Other values of measurement error, standard deviation, and sampling intervals would yield similar results. And this is the approximate threshold above which the more sophisticated IMM estimator is consistently superior due to its adaptive bandwidth or dynamic range capability. And this is the factor that matters. And the IMM shows ability to adapt via the mode probability update to keep the estimation errors consistently low, but during maneuvers it increases the bandwidth, so has them low during the uniform motion and as low as possible during the maneuvers. In summary, based on these observations, it is recommended that the threshold of 0.5 BD1 to be used as a guideline in making a choice between the Kalman filter and the IMM estimator. A minor error I want to correct. The plots for figures 11, 8, 1, 3 and 4 are switched both in my previous presentation as well as in the book. This is not for the uniform motion, this is for the maneuvering intervals, and this is for the uniform motion. Here it is constant. You can see that during the uniform motion, regardless of the maneuvering index for the maneuvering interval, the IMM performs the same, while the Kalman filter significantly degrades during the uniform motion. There is a slight degradation in velocity in the IMM, but much more for the Kalman filter. So the two plots from 11.8.1, 3 and 4 have to be switched, and the captions, the titles of the figures are correct.